Okay, so let's do a quick recap of what we've seen so far. We started out with this so-called fundamental theorem of binary classification, which basically said that a given hypothesis class is agnostic pack learnable if and only if it satisfies the uniform convergence property, and that can happen if and only if the VC dimension is finite. And in the context of binary classification with 0-1 loss, agnostic pack learning is equivalent to just pack learning the concept class itself. So if the hypothesis class is pack learnable, then it's also agnostic pack learnable and vice versa. Right? This is true specifically for binary classification with 0-1 loss. But towards that, we derived a generalization bound for an arbitrary supervised learning problem with bounded loss functions in terms of the Rademacher complexity. Right? So given any supervised learning problem, you now have a bound on the epsilon delta error and therefore a bound on the sample complexity to achieve a particular epsilon comma delta error. Right? As long as the loss function is bounded, this holds. Now computing the Rademacher complexity may not be easy, so you have to specialize this. You have to further upper bound the Rademacher complexity in terms of other parameters that purely depend on the hypothesis class itself. The Rademacher complexity, unfortunately, also depends on the distribution in consideration. So you want some kind of an upper bound on the Rademacher complexity purely in terms of some measure of the hypothesis class. And for binary classification, we saw that can be done using the VC dimension. And at the end of the last class, we had the following theorem which said that if you have a binary classification problem with 0-1 loss, then for any h, the probability that even for a single h, the generalization error is greater than the empirical risk plus some quantity, square root of 2 log ne over d by n by d plus log 1 over delta by n, this probability is less than or equal to delta. Right? And since for a given delta, this particular quantity, which was our epsilon, the deviation from the empirical risk, this goes down to 0 as n tends to infinity. The second term decays as 1 over square root of n, whereas the first term decays as square root of log n by d by n by d. Right. And it turns out that this dependence on n by d is more or less tight. It's possible to prove a lower bound which says that for any learning algorithm that outputs some predictor hs, the probability that this achieves a generalization error greater than the generalization error of the best predictor plus square root of d by 320n, this is always going to be greater than or equal to 1 over some constant, 1 over 64. Right? So it's not possible to improve upon this except perhaps by a log factor. Right? Maybe it's possible to derive a tighter bound where this log factor is missing, but that's about it. You can't significantly improve over this particular term in the denominator. Okay. So now we have at least a fair understanding of binary classification when the VC dimension is finite. Right? We know that it is agnostic pack learnable, and if you are ever posed with a binary classification problem, then you should just go ahead and employ empirical risk minimization. That's the right thing to do. But then if the VC, suppose you take some particular hypothesis class which appears very good to you, but as it so turns out, the VC dimension is infinite. Then is everything lost? Does it mean that you have to completely discard this hypothesis class and instead look for a smaller subclass? Or is it possible to still achieve some level of learning? Maybe slightly weaker guarantees. Maybe it's not possible to do agnostic pack learning, but is it possible to achieve at least some relaxed guarantees with this particular hypothesis class? All right. So that's precisely what we want to address in today's class. So the problem is the following. Suppose that the VC dimension of H is infinite. Is everything lost? What can we do? Now, in general, for an arbitrary hypothesis class where the VC dimension is infinite, you won't be able to do anything much. In this, for example, if H is the space of all possible functions from the potentially an infinite domain to 0, 1, then there isn't anything much you can do. There's a more general version of a no free lunch or another no free lunch theorem, which says that you can't really achieve any form of learning. But there are other classes of hypothesis classes for which you can actually achieve some level of learning, even if it's not agnostically pack learnable. All right. So let's recall that for pack learning, what did we want? All right. For agnostic pack learning, we basically want to make sure that for every epsilon and delta, we can make sure that the probability, so we want to make sure that there exists some learning algorithm which outputs a HS such that the probability that this is greater than or equal to R of H star plus epsilon should be less than or equal to delta. Right? We should be able to achieve any arbitrary epsilon and delta that satisfy this, provided that the number of samples is large enough. So we want, let me take the positive version of this particular statement. The probability that this is less than or equal to this is not required really, is at least 1 minus delta for n greater than or equal to n h of epsilon comma delta. Right. So this is, by definition, this is what agnostic pack learning means. I'll write this in a sort of equivalent fashion. It's equivalent to saying that there exists some learning algorithm that outputs a HS for which the probability that R of HS is less than or equal to R of H plus epsilon for all predictors is greater than or equal to 1 minus delta. Remember that this H star is the one that achieves the least generalization error. So by definition, R of Hs should be less than or equal to R of H plus epsilon for every predictor in your hypothesis class. Okay. I've done nothing so far except just a restatement of what is already above. So now suppose that the VC dimension is infinite, then it's not possible to achieve this, right, for any finite NH of epsilon comma delta. But suppose someone gives you a certain number of samples, then is it possible to at least guarantee that it's not possible to do better or epsilon close to the best predictor in your entire class, but maybe what we can hope for is that R of Hs is less than or equal to R of H plus epsilon, at least for a large subclass of predictors within your hypothesis class. Okay. maybe you are not doing the best you can with respect relative to the entire hypothesis class, but because you have a certain number of samples, maybe you can do at least as well as a large subclass of predictors, depending on how many more samples you have. If you get more samples, then maybe you do at least as well as a slightly larger subclass. If you get more samples, then an even larger subclass, and so on and so forth. Right? That's what we can at least try to hope for. Right? So
is the last equation with respect to VC dimension H is equal to infinite?
I don't know. This statement is by definition what we mean by agnostic pack learning.
The second equation.
Right? So if the VC dimension is infinite, then we cannot achieve this.
Yes.
Right?
It won't be for all H.
Correct. So we cannot achieve this if the VC dimension is infinite. So is it possible to do some kind of non-trivial learning even when the VC dimension is infinite? That's the question we want to ask. So I'll give a formal notion of what is called non-uniform learnability.
So you said that you want to do it for a large number of hypotheses.
I'm sorry?
Large number of functions on the hypothesis.
Correct. So it's at least as good as the best among a subclass of your hypothesis class.
Then why can't you make that subclass your hypothesis?
You can't, right? Because the VC dimension is infinite.
What does that have to do with restricting your subclass?
So if the VC dimension is infinite,
You can't.
then using a finite number of samples, it's not possible to achieve a generalization error that is close to, it's not possible to achieve a generalization error that is close to the least generalization error within your class. Right? Or in other words, in this case, you want to be at least less than or equal to R of H plus epsilon for every H. Right? But if the VC dimension is infinite, using any finite n, it is impossible to achieve this. Right? Because if I could, then it would mean that the class is agnostically pack learnable, which cannot happen if the VC dimension is infinite. So if the VC dimension is infinite, maybe I can relax this particular condition. Maybe I don't want R of H's to be less than or equal to R of H plus epsilon for every single H in H. Maybe I'm okay with, if this is true, for all H within a subclass, where this subclass depends on how many samples I have. And the size of this subclass keeps growing as the number of samples I get keeps increasing. Right? So maybe what I want is maybe a family of subclasses, H1, which is perhaps a subset of H2, which is a subset of H3, and so on. And maybe I'm happy with deriving a predictor or a learning algorithm that outputs a predictor for which R of Hs is less than or equal to R of H plus epsilon for all H in Hn. Alright, I don't do as well as the best predictor in the whole hypothesis class, but I want the best predictor within this subclass, at least the best predictor within a subclass. So that as I keep increasing the number of samples, I can potentially do better and better, because I have this property that H1 subset of H2, subset of H3, and so on.
Choosing the subclass in hypothesis
always depends on my number of samples, or is one of the dependency that have?
Maybe I didn't follow. What do you mean?
So we are dependent. The hypothesis class is dependent on number of samples.
Number of samples, yes, because that's the only parameter that we have flexibility with, right?
Yes.
Right now we are measuring complexity with respect to how many samples you need to achieve a particular epsilon and delta. So one way is to say that maybe relax what we want on epsilon and delta. But for now, we want an arbitrary epsilon comma delta error. How many samples do I need to get arbitrary epsilon comma delta error? Right? When I say epsilon comma delta error, it's always relative to some good predictor. Right? You want to do good, and the goodness, how well you perform, is measured with respect to some reference predictor. In agnostic pack learning, this is the predictor which achieves the minimum generalization error. But now, we can't hope for that if the VC dimension is infinite. So maybe I want the best predictor within a particular subclass. Is that okay? Great. So let me define this non-uniform learnability. So we say that H is non-uniformly learnable if for every epsilon greater than 0, delta greater than 0, and H in your hypothesis class, there is some number nu to indicate non-uniformity of epsilon delta H and a learner outputs HS satisfying probability that R of HS is less than or equal to R of H plus epsilon for all H in your hypothesis class, such that NH non-uniform of epsilon delta H is less than or equal to N. So this probability should be at least 1 minus delta.
Why does the sample complexity depend on?
Yeah, so that's the difference here. So basically, I'm saying now that the sample complexity, I have a separate sample complexity for every H. So if I removed this particular H everywhere, then you see that it's equivalent to agnostic pack learning. All right. So by definition, a hypothesis class was agnostically pack learnable if for every epsilon and delta greater than 0, there is some n that depends purely on epsilon and delta and a learning algorithm such that R of Hs is less than or equal to R of H plus epsilon for every H in H with probability. So this probability is at least 1 minus delta.
Why not to take the max over the H in that?
What do you mean the max over H? So right now, okay, so let's look at it the following way, right? So let's define H subscript n, okay, as, so suppose that some hypothesis class is non-uniformly learnable according to this particular definition. Okay, let's try to state this definition in a slightly different manner. So suppose that Hn is, now remember that for every H, for every epsilon, delta and H, I'm associating some number. Let's call it NH, Nu of epsilon, delta, H. Okay? So Hn is the set of all H in the hypothesis class such that NH, Nu of epsilon delta H is equal to M. Okay, or let me put it in another way. Epsilon delta H is less than or equal to M. Now you agree with me that H1 is a subset of H2 and so on, right? And the union of all of the HIs, that gives you the hypothesis class H itself. Because a fundamental assumption that we're making is that for every H, this quantity is finite. So when I say there exists an NH, implicitly I'm saying that this quantity is finite for all H. Okay, so we have the property that H1, so this is an increasing family of subsets, and union n equal to 1 to infinity, Hn is equal to H. So then this particular statement here is equivalent to saying that, so suppose that in each such family, let Hn star be the one that achieves the least generalization error. So Hn star is the R min R of H for H in the nth hypothesis subclass. So then the statement is, you can easily see that this that the statement above is the same as saying that R of Hs is less than or equal to R of Hn star plus epsilon with probability at least 1 minus delta. In the case of pack learning, for every epsilon, okay, so in the context of pack learning, we didn't really care what happened for every single n, but beyond a certain n, beyond a certain value of n, for a given epsilon and delta, we wanted to make sure that this Hn star was equal to H star, right? So right now what we are saying is that given any finite number of samples, maybe it is impossible to get epsilon close to H star itself. But then I'm going to define certain targets for n equal to 1, n equal to 2, n equal to 3, n equal to 4, and so on. I'm going to have certain families of subclasses such that I do the best with respect to this particular subclass. Okay. Now in this, it may help to think of a concrete example. All right, let's take the family of all possible polynomials of all degrees. Right? Take H to be the set of all polynomials over R. Okay, and I'll define the following subclasses. Now you shouldn't think of these subclasses as exactly the Hn that I have defined over here, but let me call it maybe H prime 1 or H prime k is the set of all polynomials of degree less than or equal to k. So you agree that this is a growing family of hypothesis classes, which eventually encompasses all possible polynomials, right?
Why did you use the prime again?
Well, because in this example over here, when I said Hn, the subscript denoted the number of samples, whereas here the subscript essentially denotes the degree, right? The correspondence need not be one-to-one. And it should be noted that this Hn, when I say Hn over here, this depends on epsilon and delta. All of this, the family changes as you change epsilon and delta. Okay. But in this case, it's purely dependent on this parameter, the degree. All right. So Hk prime is an increasing family of predictors, and which includes all possible polynomials. Now, what can you say about a specific Hk prime? What do you know about this? Or
There must be some H star in the subclass.
that's true, but let me be a little more precise. What can you say about the VC dimension of each of these Hk primes? It's all finite, right? And the VC dimension is increasing, right? As you increase k, the VC dimension increases linearly, in fact. Now H is a hypothesis class with infinite VC dimension, but each of these Hk primes is a hypothesis class with finite VC dimension, correct? So it means that for a given epsilon and delta greater than 0, if the number of samples, so let's say that, so this has, so each Hk prime has finite VC dimension, and therefore the n, let's say, NH, let's call it NHK for now. So this quantity is finite. All right. So one approach is, let's say that given a certain number of samples, I'm only going to target being the best within this particular subclass. If I have more number of samples, then I look at a higher degree, and so on. But it doesn't mean that I'm only going to learn from within Hk prime. All right? When I say non-uniform learnability, I want to do at least as well as the best predictor within this particular subclass. But my predictor itself need not come from this subclass. It could be from a higher subclass. But it should achieve a generalization error that is at least as good as the best within this subclass. All right. So in this specific example, I want to devise a learning algorithm which does the following. So given a certain number of samples n, right, there's an associated k of n as well with this particular n. I want my learning algorithm to output some polynomial of degree anything. It could be less than k, it could even be greater than k. But with these n samples, it should do at least as well as the best polynomial of degree at most k. Okay, the generalization error of my predictor could have any arbitrary degree. It could be a polynomial of degree greater than k or less than k or anything. But the generalization error of my predictor should do at least epsilon at least as well as the best kth degree polynomial. Okay, it could do better, but at least as well as the best kth degree polynomial. That's what we are aiming for in this case. We can't do as well as the best possible polynomial because it's not pack learnable. But as you increase the number of samples, the degree k also improves. It also increases. All right. So that's what I mean when I say that the hypothesis class is non-uniformly learnable. All right. Any questions?
What is the sample complexity
Yeah.
in non-uniform?
So it's precisely this, right? As long as n is the number of samples is greater than or equal to this particular quantity over here, you're guaranteed that your learning algorithm outputs something for which r of hs is less than or equal to r of h for all r of h, for all h whose sample complexity. In this case, it's not, I wouldn't call it the sample complexity as such, it's some number.
Why aren't both the problems equal, diagnostic, path learning, and non-uniform? Because as you make n go to infinity, they're essentially
Correct, but there may be no such n for which this includes all possible h. So in agnostic path learning, I wanted to make sure, I basically I don't want this h to be present. Right? It has to be hold true for every single h. But for any finite n, it may be impossible to make sure that, so if this,
there are classes which you can't
for which, and
create such.
for example, let's take this very specific example of the set of all polynomials. Clearly, this is not agnostically path learnable. You agree with that, right? But then, according to this definition I have over here, it is actually non-uniformly learnable. And why is that true? Well, here is one such learning algorithm. Right? For every k, for every possible k, I know the corresponding sample complexity. You agree with me, right? So then, given a certain number of samples, I'm going to choose the largest degree for which the sample complexity is less than or equal to n. And I'm just going to do empirical risk minimization on this hypothesis class. I'm just going to ignore everything else. I'm going to pick a specific subclass depending on the number of samples I have, and I'm going to do agnostic path learning, just do empirical risk minimization on this class. All right. Then by definition, I know that this predictor is going to achieve a generalization error, which is going to do at least as good as the best k degree polynomial, because that's how because the class of k degree polynomials is agnostic path learnable. So therefore I can achieve an epsilon delta error. Right? So, and that's precisely what we wanted here. That's precisely what is required in the context of non-uniform path learning. If you get more samples, then you choose a higher degree. If you have fewer samples, then you choose a smaller degree.
Where is the problem non-uniform?
So we'll see that in just a minute. Okay, but at least in this case, it's believable. Right? You can convince yourself that at least this hypothesis class, which is not agnostic path learnable, is non-uniformly learnable because you have a learner that can achieve this particular definition of learning. Right? So going to the question of when is a particular hypothesis class non-uniformly learnable or not. So H is non-uniformly learnable if and only if it can be expressed as a countable union of agnostically path learnable classes.
These classes have some hierarchy between them. Can be
It can be anything. You can impose a hierarchy later, but like as long as it can be expressed as a countable union of agnostic path learnable classes, you can in fact impose a hierarchy on them.
So in the previous example, how do we know that H prime K, the countable union of H prime K will use H?
So what is the set of all possible polynomials? All degrees, right? And by definition, you can get any degree polynomial. So take any polynomial in H. It should have some finite degree, right? Which means that it should belong to some possible HK prime. All right. So one thing you have to keep in mind is that H is not equivalent to the set of all power series. There's a difference between the two. All right, so there's a different set so if you take some, let me call this H double prime as the set of all H of x that can be expressed as summation I equal to 0 to infinity ai x to the power I, where ai in R, right? And the ai should satisfy some regularity properties. This is not the same as the set of all possible polynomials. This is the set of all formal power series. Okay. Now this is not, I don't claim that this is non-uniformly learnable. I'm sorry?
Why aren't they?
Because this by definition is not a polynomial and it's not well defined for all a comma. So if I give you give a particular AIs, right? This is not well defined over all possible R. Because the right hand side can potentially diverge. But on the other hand, if you take any polynomial, a polynomial has to have a finite degree, which is well defined over all of R.
So this is a subset of that.
So the set of all polynomials is a subset of the set of all formal power series. Because for a polynomial, AI is equal to 0 beyond a certain k. So that's why this is not, I'm using this loosely because it's not well defined for all possible A1 through A, all possible AIs, right? Because this need not converge. This depends on, this could potentially converge for some x and not and diverge for some other x. But on the other hand, a polynomial is defined over all of R. Right.
Can I comment anything on hypothesis class is uncountable or countably finite?
So, I mean, this is, what kind of hypothesis class is this? It's uncountably infinite, right?
But from the theorem, I'm seeing the countable union of.
It's a countable union of agnostic pack learnable classes, but each pack learnable class may be uncountable. For example, even this hk prime, all polynomials of degree less than or equal to k, that's uncountable.
Yes.
Right? So uncountable doesn't necessarily mean that it is or it is not agnostically pack learnable. Even if something is countable, it doesn't mean that it is agnostic pack learnable. Right? There can be countable hypothesis classes which are not agnostically pack learnable.
So when we claim that we are taking the set of any degree k, like polynomials of any degree k, so wouldn't there be a point where we'll reach this h double dash?
So So by definition, H is the union of hk prime over all k equal to 1 to infinity.
So then that becomes almost equal to this h double dash.
Almost, but it's not.
Where would we write such a difference?
So-
just choose some finite, like x1 squared plus x cubed.
Correct. So this is,
That will diverge, could be possible.
yeah.
If you have x1 plus 3xy plus 4x cubed, x1 with 1 only, right? It has to be equal to some finite value. But there the RHS could be some divergent thing, it can never converge.
But that would be
Okay. So let's take one. Let's say that AI is plus 1, or take any particular H in H double prime, where AI is non-zero for every I. All right. Let's assume that AI is 1 for every I. There exists no polynomial which is equal. So this cannot be expressed as a polynomial, right, of any degree.
But when we are claiming that we are taking the set of like union of all possible k degree polynomials,
Correct.
then is that here are we implying that k is like
Finite.
or
Finite but
completely
not
infinite?
finite but not bounded. So there's a difference between bounded k and finite k. Right? So this is basically the set of all polynomials with bounded degree. This is the set of all polynomials with finite degree. Whereas this is, okay, it's not really polynomial, but power series with no bound on it, with unbounded degree. Right? Okay. Any other questions? Okay, so I won't formally prove the theorem, but you can see why this is true. So suppose you can express it as a countable union of agnostic pack learnable classes, then there should be again, we're only focusing on binary classification with 0-1 loss. So which means that if it is agnostic pack learnable, then it satisfies the uniform convergence property and it has finite VC dimension. So if it can be expressed as a countable union of agnostic pack learnable classes, then for each of these classes, these agnostic pack learnable classes, there is an associated sample complexity. Let's say sample complexity of uniform convergence. All right. So given n, you can restrict yourself. You know that if you choose the best among this particular subclass, then you can then at least within that particular n, you know how well you're going to do. Right? You know that the empirical risk is going to be close to the generalization error, at least for all h within this agnostic pack learnable class. Outside, we don't know what may happen or what may not happen, but at least within this subclass, we know that the empirical risks are all going to be close to the generalization error. So therefore, it's plausible that h is non-uniformly learnable. It's similar to the argument that we made for the set of all possible polynomials. All right, and similarly, the reverse also is a bit believable by this definition. Right, if you take this possible definition, effectively, like going by this definition, you should be able to decompose it into a sequence of countable classes, h1, h2, h3, and so on. And every predictor little h should belong to one of these capital H, some hi. Right? So if you just look at this particular definition, effectively we have expressed h as a union of countably many classes. And if you think about it, each hi should be agnostically pack learnable. Because by definition, we are saying that there exists a learning algorithm such that this happens. You can get, as long as the number of samples is at least little n, you have a learning algorithm that outputs a predictor which gets epsilon close to the best within the hypothesis class h sub n. All right. So, but what this theorem also says is that, yeah, so that's a good thing and a bad thing. The good thing is that if you can express it as a countable union of agnostically pack learnable classes, such as the set of all possible polynomials over R, then you can at least do a relaxed notion of learning. It's not agnostically pack learnable, but it's at least non-uniformly learnable. But if it cannot be expressed as a countable union of agnostically pack learnable classes, then there's no hope. You can't even do non-uniform learning. So for instance, if let's say that the domain is infinite, it could be countably infinite or uncountably infinite, and your hypothesis class is the set of all functions from the domain to 0, 1, then H is not non-uniformly learnable. This is a fact.
say comment on a path learnable, or is there any other way other than non-uniform learnable?
There could be other definitions as well, but this is already a relaxed notion. There's something even more relaxed in the sense you just want consistency. As you increase the number of samples, you just want the empirical risk to be arbitrarily close to the generalization error. All right, but that's in many cases that's a very weak requirement. Sometimes that's the best you can hope for, but we will at least want non-uniform learnability. We'll see what are the trade-offs with non-uniform learnability. Right. So if I give you an arbitrary hypothesis class that is non-uniformly learnable, in general, empirical risk minimization is not going to work. Right? You can't look for that predictor which has the least empirical risk. That's not going to give you, it's not something that will achieve non-uniform learning. So you need to devise a new learning algorithm. Right? And we'll do that, which is almost the same as empirical risk minimization. Okay. So then what do? Effectively, what we'll do is we'll do empirical risk minimization, but add a regularization term, which will say, which will basically give you a weightage. So for a given epsilon and delta, you prefer these over other predictors. So for example, if in the context of perhaps the polynomial classifiers, what you could do is you prefer lower degree polynomials over higher degree polynomials. So you add a regularization term, which biases you towards lower degree polynomials rather than higher degree polynomials. That's one way of achieving non-uniform learning. Now, in general, the way you would want to bias could potentially also depend on what kind of background information you have about the ground truth. Right? Maybe the ground truth itself cannot be described by a low degree polynomial, but you don't have enough samples. Maybe it can be described by a polynomial of degree 100. Maybe you know that, or maybe you know that the degree is likely close to be 100. In which case you may want to bias yourself towards polynomials of degree close to 100. You're not sure, but you have some background information. So we'll do that in a slightly more systematic fashion. So let's suppose that you can write H as a union k equal to 1 to infinity hk, where each hk is path learnable and therefore satisfies the uniform convergence property. No. So the set of all formal, what kind of functions can you possibly generate with the set of all formal power series? Yeah? Yeah, but what if it's not continuous? You can't generate a discontinuous function using this, right?
I'm not sure because you can go to infinity, right? So you can like generate one by 1 minus x with this, which is sort of this.
Yeah, but let's say I want the threshold function, which is 0 for x less than 0 and 1 for x greater than 0.
And this is equivalent to the Fourier thing also, so that you can do.
So the Fourier series or Fourier transforms can't approximate any arbitrary function. You need at least certain integrability guarantees on the function. Okay, we're probably deviating from that, but you can look, the best in many cases what you can do is merely approximate functions, but not get an exact representation of every possible function. I mean, this is an even weaker space, but yeah. So also, I mean, this set of formal power series, this is not necessarily even a function, right, for arbitrary AIs. It's so each of these could only be defined within a certain range.
Why is it not a function?
Well, by definition, a function has to be, so if it's a function over R, then the function has to be well defined over all of R, which means that this has to converge over all of R, which is not guaranteed for an arbitrary choice of AIs. Right. So you at least need something like absolute summability in order to ensure the convergence. Okay, so suppose that I have this hypothesis class which I can write as a countable union of agnostically pack learnable classes. So it's non-uniformly learnable, and therefore I can represent it in this form, where each HK has finite VC dimension and also satisfies the uniform convergence property. Let's assume that n UC k of epsilon comma delta, that's the sample complexity for achieving epsilon delta uniform convergence, right? So which means that as long as n is greater than nkuc, I have probability that R of h minus Rs of h, the empirical risk minus the generalization error, is less than or equal to epsilon for all h in hk, probability at least 1 minus delta for k, if the number of samples is at least nk uc of epsilon delta. I'll also define, an equivalent notion. So in this case, what I defined was the smallest n such that you can achieve epsilon delta uniform convergence. But for a given n and given delta, I can also say how close is epsilon, how small is epsilon going to be, right? So let's define epsilon k of n delta to be the smallest epsilon is less than or equal to n. Right, so in other words, for a given n and delta minus Rs of h is guaranteed to be less than or equal to epsilon k of n delta for all h in hk with probability at least 1 minus delta. Okay, so this is So let's choose a WK. K. Sorry, a HK. So the hypothesis, so I'm writing this H is a union of HK. So that's why now the subscript K will denote the kth hypothesis class. And this K is different from the number of samples N. Okay. N equal to 1, 2, and so on. So this is what I call a weight function. Function such that Wk is greater than or equal to 0 for all k, and the Wk's the series is less than 1 or less than or equal to 1. So I choose a weight for each hypothesis class, each hypothesis subclass. So it's a non-negative weight, and the sum of the weights is less than or equal to 1. Okay. Then what I'm guaranteed is that we know that for every k, for a specific k, the probability that R of h minus Rs of h is, say, greater than or equal to epsilon k of n delta times Wk for even one h within the kth hypothesis subclass is less than or equal to delta times Wk. Right? I mean, it's just a restatement of what I have over here, except that I've replaced delta with delta times Wk. Right? Both here as well as here. Nothing else. And I've sort of taken the negative version of this particular statement. This says that with high probability, the empirical risk is close to the generalization error, and this says that with very low probability, the empirical risk is far away from the generalization error. Okay, so I have this. Right, this is true. There's nothing special over here, but now if I want, okay, suppose that I want agnostic pack learnability, then in a sense all I want is that this should hold true. I would want this to hold true for every h, for every k and every h in hk. So probability that R of h minus Rs of h greater than epsilon k of n times Wk delta for even one h in h. So maybe let me define before I do that. Let me define the following. For any h in the hypothesis class, let's define k of h as the smallest k such that h is in hk. Such that h is in hk. So a particular predictor could lie in multiple hk's, and you're taking the first possible subclass where this predictor belongs to. Basically what I've said is that within each subclass, all of the empirical risks are epsilon close to, epsilon k close to, for the kth hypothesis class, the empirical risks are close to the general, epsilon k close to the generalization errors. All right. But I want to make sure that this holds true for all possible k. Right? And for that I can just use a simple union bound. So this is equal, this is basically the probability union over all k right, which is less than or equal to the sum of those probabilities but we know that this is upper bounded by wk times delta. And we've specifically chosen the weight function so that they sum to something less than or equal to 1. So this is less than or equal to delta.
Are those two equal or is it the first and the second?
Which one?
The first and the second one.
Uh, why are they not equal?
Sort of doing it for each edge, you're checking if you're finding the problem with that
Um, sorry, which one are you?
the first two lines.
The first two lines, yes. You would be okay with this, right? Very good.
I'm confused with this that.
Um, fair enough. They could be different because it's possible that for a given h, which belongs to two different k1, k2, this could be satisfied with respect to k1 but not with respect to k2. Fine. All right. So, so basically what this is saying is that if I have n samples, then I can make sure that for every h, the empirical risk is epsilon k of h close to the generalization error with probability at least 1 minus delta. All right. So this leads us to this new learning algorithm, which I'll call structural risk minimization. Which basically does the following. So given S, Hs is arg min over all H within your hypothesis class of the empirical risk plus an additional regularization term, which we will choose to be epsilon k of H of n wk of h times delta. Right, so now we are fixing a particular target delta, right? And for that given delta, and you know n, you are going to choose that predictor that minimizes the empirical risk plus a regularization term, which is precisely epsilon k of h. All right, with this wk's, they are guaranteed to, the weights wk's are chosen so that they're all non-negative and they sum to something less than or equal to 1. So let's suppose that we run this structural risk minimization algorithm, then what are we guaranteed to achieve? Then we know that okay, so this is our algorithm. What can we say about R of Hs? So firstly, R of Hs is going to be less than or equal to Rs of H plus epsilon k of hs n wk of hs times delta. Right? This just follows from the uniform convergence property that we had over here, because this holds true for every single h, and hs is just one such predictor from the class. Right? So importantly, we had this. So basically, what we showed was probability that r of h minus rs of h is less than or equal to epsilon k of h of n wk of h delta for all h in h, and this happens with probability at least 1 minus delta. That's what we showed previously. So this guarantees that this also happens for hs. All right. But by definition, this is the one that minimizes. So if I call this quantity the structural risk, then by definition hs is the one that achieves the minimum value of this particular quantity. All right. So this is less than or equal to rs of h plus epsilon k of h and wk of h times delta for all h in the hypothesis class. All right. Since hs minimizes star. So let me call this double star. Then from that, I also know that rs of h is right. So it's true that if I have enough number of samples, then this is also less than or equal to r of h for all h such that epsilon kh of n, let's say plus epsilon kfh times delta less than or equal to epsilon. Or equivalently, nuc k of epsilon comma delta is less than or equal to n. Which is exactly what we wanted in a non-uniform learning algorithm. Questions? Okay, so maybe let's stop here. We'll continue in the next class.